Alright, we'll continue our discussion on bolthead connections. Now let's discuss the derivations and code provisions regarding this member or this joint. Now let's talk about the limit states. Again, as I have already introduced this in the introduction of steel structures, that limit states there is something like a limiting value or something like a, a basis for the analysis that we should prevent our member or our joint to reach those failures. Or you, you can just think of it as something like a failure, um, possible failure mode. And we are going to design the members or joints that it will not reach this failure. So in bolted connection, we can have um, shearing failure of bolt, and we can have bearing failure of plate, and the tensile failure of bolt, and we can also have shear failure of plate. Okay, so shearing failure of bolt, meaning that the bolted connection, what failed is the bolt itself. So this type of failure is you have already encountered this many times, and even in our topic on um, tension members. So for example, we are applying loads, then this bolt is actually, it can fail that. For example, we have a weaker, or let's say our bolt is not enough, or does not have enough capacity for for these loads, then it can fail in shear. The bolt itself can fail in shear. For the bearing failure of plate, if you try to look at the top view, for example, or let's draw a three-dimensional um, illustration here. Now it is possible that um, what if in this connection we have a weaker plate and then the bolt is strong enough, then it's possible that when you apply the loads, then it's possible that this, say we have bolt here, it's possible that the bolt will actually push this plate, let's say in this direction. So if you draw it in let's say in plan view, then it's like this. So it will be instead of having a perfect circle hole, it will start to um, something like um, something like elongate. Okay, so it starts here, the bolt starts here, but because of the load, it ends somewhere right here, and then it's actually pushing this hole towards that direction. Okay, so meaning that the plate itself is actually um, failing in in bearing. Okay, so that's one failure. Now another failure is the tensile failure of the bolt. So just like the shear failure, that it is possible that this bolt, when it's under the tensile loading, it could fail in tension. So and this one, the shear failure of plate, instead of having a bearing, it is possible that the bolt hole will actually something like rip off, something like this. Okay, so something like a block shear, but it's gonna um, break over here. So that's the shear failure of plate. Okay, so now let's discuss um, the bearing capacity of holes, of bolt holes. Okay, so bearing capacity of bolt holes, again, when we say bearing capacity, that refers to the base material or plate materials, and it's not the bolt itself. Okay, so the equation that we have is actually we have uh, we're we're actually given by this equation 0.6 Fu LC L sub C times D. So this is our nominal strength or resistance R sub N divided by 2. It's because of this failure surface that, I guess, let me draw this in a three-dimensional view. Now it is possible that the failure here is the let's say this area, this bearing area, and this bearing area, let's draw it completely. So let's say this is the bearing area, but towards here you can also feel along this area, right? So something like this. So this distance from the edge of the bolt hole to this edge, that's our clear distance. So L sub C times D, that's the thickness. So let's say this is the thickness. Okay, let me try it again one more time. Okay, so it's something like this. So this area, we have this thickness. It has the same thickness as this. So that's D, and the distance is the clear distance. So basically, this is the area LC times thickness, and this 0.6 Fu is actually relating to the shear. The 0.6 value is the something like the shear constant, if we can say that. And this one is the tensile strength of the material. That's divided by 2 because you're actually the capacity would be 2 times because we have two shearing area here. Okay, so that's one equation, but this is not yet the main equation, right? Another equation is given by this: Rn is equal to C, so some constant times d times Fu. Now um, this one is the area, but that's gonna be the projected bearing area. So this is D. Okay, so let's say the diameter of these bolt, or maybe the bolt hole. I'm not sure yet. I'll check the notes later. And then this one is the thickness. Okay, so this is the projected area. And then we have this constant. Now, they're actually combining this, and finally we have this given equation: 1.2 L sub C D Fu, or must be less than or equal to 2.4 the bolt diameter times D times Fu. So this is now the equation. However, we can also rewrite the equation in a much simpler terms, or let's say simpler expression, as 1.2 um, D times the Fu times the minimum of either LC and 2 times the bolt diameter. Okay, so in our calculations we will use these expressions. This is just like the same as the bolt shear equations that we have discussed in the previous topics, because the actual expression is given in this manner, that we just converted it or transposed it into two limiting conditions, something like this: minimum of LC or 2 dB. Okay, so now let's write the notations. On the D is the thickness of the plate, and that's in mm, and Fu, that's gonna be the ultimate strength. And of course that's going to be the ultimate strength of the plate, not the bolt. Okay, so take note, that refers to the plate. And the LC is the clear distance, and this dB is what we call the bolt diameter. Right, now what is this clear distance? This clear distance is actually taken as, or let me draw first. Now, for example, we have this bolted connection. Now, the clear distance is actually this distance. So this is LC. This is another LC. So let's just write LC2, and then this is LC1. So meaning that the clear distance is basically from the edge of the hole, of the bolt hole, to the edge of the plate, or from edge of the bolt hole to the adjacent bolt, adjacent edge of the bolt hole. So that's going to be our clear distance. Now, how do we obtain this? We're actually given in the drawings, or in our homeworks, we're actually given by this distance from center to the edge, center distance, center to center distance of bolt holes. Okay, so um, let's notate this: the distance from the bolt hole to another bolt hole, that's going to be the interior distance. So let's say that's Li, and this distance from the center of the bolt hole to the exterior portion of the plate, let's just say that's Le. So the clear distance is actually the minimum of um, the minimum of these two distances. So the first one is Le, meaning, let's consider this Le minus the diameter of the hole, so dH, all over 2, of course, because you're actually given this Le minus the half of the diameter hole. But for the interior, we have Li minus the center to center minus half of this plus half of this. That's going to be minus dH. Okay, so that's our clear distance, right? So now this is our capacity, our nominal capacity, and take note, this is the nominal capacity for a single bolt. Now if you have, let's say, 4 bolts, then meaning that the capacity, you should multiply that to the number of bolts. So for example, we have 4 bolts, then you should include this and B. And now to take the factored resistance, we'll multiply a reduction factor, and this reduction factor is taken as 0.75. So this is the number of bolts. That's the bearing capacity of the plate. Now let's move on to the shear capacity. For the shear capacity, equation that we have is Rn V F and V times AB. Okay, so shear capacity, this refers to the bolt itself. Uh, that's the bolt itself. Whereas the bearing is, or the bearing refers to the plate material. Whereas this shear capacity is the bolt itself. Now, this equation says that we have the factor capacity as the shear. That's the nominal shear. Is the nominal shear stress, and this is the area of the bolt. Now, basically, it will just look like this. So let's say this is our bolt head, and we have this, let's say the body or the shank, and we have this thread. So if we are actually trying to shear this portion, then this is the area. That's the area AB. So basically, this area of the bolt is just simply the pi d squared all over 4, and of course that's going to be the nominal diameter. Again, when I say nominal diameter, it's just a way of specifying the material, although the exact geometry or the actual geometry may not be actually the same as the specified ones. Now, what is this shear, nominal shear stress or shear strength? Where can we find this? We can actually obtain this from the table. So in our lecture handouts, that's table 13-2. But it's also, you can find that in the code. Now, in the table is specified like, for example, we have a 307 bolts, then what's going to be our nominal shear stress in bearing connection. Then it says, for example, 165 megapascals, and if you have an A325 or A325M, when threads are not excluded from shear planes, then we have 330. Okay, so just a couple of notes. It says here we have planes excluded. Threads are not excluded. So meaning, what it means is that, for example, we have this this connection, and let's say this is our bolt, and okay, so let's say the threads is only up to here, and in this figure the threads is, let's say it's up to here. So you would see actually when you say threads are not excluded. Okay, so when you say not excluded, so it just means that it's just the same as saying that the threads, they're actually included in this shearing, in this shearing plane. Okay, so this one excluded from shear planes. Okay, so this one is actually excluded from shear planes. Now there's a difference in the values because for the threads, if you try to zoom up the threads of the bolt, say something like this, okay, you would notice that this diameter is different from the diameter, let's say the root diameter. That's going to be different. Okay, so that's why, of course, if you have a smaller area, then of course you have a smaller capacity. So that's just the meaning of that. Now, in our lecture handouts, there's also another table. Table 13 dash 3. There's a given example bolt size M16, and what's the bolt area? It's already computed. let's say we have this bolt size, and let's say it's M16. Okay, so take note, when we say M16, that's the 16 mm bolt in metrics. Okay, so M stands for metric, or metric designation. Then the another column is bolt area. The bolt area is given, for example, 201, simply because it's just simply pi d squared. Uh, Maybe you can also check that one. I think that's just coming from this pi d squared over 4. Okay, and then it says here another column for the shearing planes. Okay, so how many shearing planes are there? Is it just one or two? So the meaning of that is, if we have a connection something like this, and we will have a connection something like this, then meaning that the shearing planes here in this type of connection, we have two shearing planes, whereas here it's only one shearing plane. Okay, so it says here that if you have one shearing plane, then if you have a high strength bolt, a 325, and here there's a 490 M, and there's another a sub column here we have included, meaning that meaning are the threads included, or is it not? X. So are the threads included, or is it not? Now for the first one we have 49.7, but here if the threads are not included, then we have actually a higher value, 62.4. And for two shearing planes we have 99.5, and this one is 124.8. Of course, if you have two shearing planes, then of course you have a higher capacity. Why? It's because you have two areas to shear off. So greater area means that you have greater capacity. Okay, so that's all for our shear capacity. Now let's move on to the size and use of bolts. We have actually 4 hole types. Okay, so one is the standard, and second is the oversized, the third is the short slot, and the fourth is the long slot. Okay, so for example, we have an M16 bolt, then our standard size would be 2 mm larger. Okay, so meaning that, for example, we have an M16, this one is 18 mm. Let's say 18 mm. But for the oversized, meaning that it's slightly larger, then the diameter would be 20 mm. Okay, so that's just the oversized. For a short slot, when we say slot, it's actually two, let's say, two circular holes here, and it's just being converted to this something like this, to this oval area. Now if we have a long slot, then it means that we have a longer length here. Okay, so the values of this, the values of the diameter, or the distance, or the length, the width, this one is measured in terms of width and I think length, and the length, I'm not sure if it's in center, but we can just refer to our lecture handouts or the code. So that's in terms of width times length. Now the value of this, the numerical values of these can be found in NSCP. Okay, so now let's discuss the minimum spacing. The minimum spacing required by the code says that it should be S is equal to 8/3 of the bolt diameter. But preferably that should be 3 times the bolt diameter. 8/3 is something like 2.6 or so, less than 3. So it says that although this is the ones that's being specified directly, but this one is a more it's just a preference. Okay, so minimum spacing is 3 times the bolt diameter. So meaning that if we have this connection, then the minimum spacing right here should be 3 times the bolt diameter. So 3 times this, that's going to be the distance. Okay, so now let's move on to the minimum and maximum edge distance. Or I guess we should discuss first the max spacing. So if we have a minimum spacing, then we also will have maximum spacing. So X max is maybe this is 24 times the thickness of the plate, or 300 mm. Okay, so this refers to if it is if this is painted or unpainted, but not subject to corrosion. But for other conditions, the S max is equal to 14T. Okay, so subject to corrosion. Okay, so that's going to be the spacing. Now the edge distance, the minimum edge distance, minimum or maximum edge distance. So meaning, for example, this is our plate and this is our bolt. Then what's going to be the minimum here? So we'll have the minimum, the L minimum. This can be obtained from the table. Okay, so we have in the table in, let's say, 13-5, we have a bolt diameter in the first column, and then we have a second, in the second column we have a sheared edge, and here we have rolled edges, etc. Okay, so for example, we have 16 bolt diameter, then this one is 28, and this one is 22. That's in mm. Okay, so what it means at sheared edges, if this member, or let's say this material is being cut using the sheared or any shearing action, then that's going to be this. But if it is cut, let's say thermally, let's say using acetylene tools or something, there's rolled edges and some details here. It says thermally cut. Okay, so the value of the minimum is 22. Now for the maximum, LE max, this is LE mean, L sub E mean. L sub E max is equal to the minimum of 12T, that is 150 mm. Alright, so that's all for our code provisions. Now we will be able to appreciate this or see the picture when we are actually applying it in a sample problem. And that's what we're going to do in the next video.